Okay, we're going to continue working a few questions from the practice exam. So this is question 5. And we have this function which is given by this power series. So f of x is the sum from n equals 0 to infinity of minus 1 to the n to n plus 2 to n factorial x to the 2n plus 2, and its derivative is, and then we have a bunch of options. So option A is x e to the x. Option B is x e to the minus x. Option C is sine of x. Option D is x sine of x. And option E is x cosine of x. Okay, cool. Let's think about what this question is requiring from us. So we have an explicitly given power series. It's given by this thing. One of the things I've said many times, and one of the key points about power series, is that they are just as good as polynomials in the interval for which they converge. This guy will actually converge over the entire real line because of this n to n factorial, but we don't need to worry about that. If we're not told anything about the interval convergence, just assume it's not an issue. It converges wherever you want it to. So this guy is just as good as a polynomial. We can do anything we want to it that we can actually do for a polynomial. And if we were differentiating a polynomial, it would just be trivial. We just differentiate each term, right? We just go through and differentiate each power of x, and that's what we can do with this power series. So actually finding its derivative as a power series is a very easy thing, okay? But it is asking us, its derivative is these things, these bunch of functions. These are explicitly given functions, they're not power series. However, all of these guys are guys that we actually recognize we can find the power series of, right? Because we know the max series of e to the x, of sine, and of cosine, right? These are the standard max series that you have to learn. By learn, I mean work out a few times and know them. So if we have the max series for e to the x, we multiply through by x, then we have another max series. It's easy to identify it. Same for e to the minus x, same for x sine x, x cosine x, right? So all of these guys are explicitly given max series that we easily can work out. So this question is just about whether or not, well, it's testing whether or not you know that you can differentiate a power series term by term, and it's testing your knowledge of these basic max series and the fact that if you have a max series, you can multiply by x just like in a polynomial. So it's a reasonable test of all these important properties of power series and max series. So let's just do it. So first we're just going to differentiate this guy. So f prime of x, n equals 0 to infinity. So we take the derivative through and apply it to this x to the 2n plus 2, right? Just like if we had a polynomial. Right? So then what would we have? We'd have 2n plus 2, and then x to the 2n plus 1. And then these two n's plus 2 would cancel here and here. And what we got? We've got this series. We have minus 1 to the n, 2n factorial, and then this. So it's not looking like anything we recognize, right? But hopefully with some experience of these standard max series, what should come to mind is that if we had minus 1 to the n over 2n factorial and not this plus 1, then this should just be the cosine max series, right? So if we just factor out the x, then we have this thing, minus 1 n x to the 2n over 2n factorial, and this is just the max series of cosine. You have to know this at this point. So it's x cosine x, and that is option E. And that's it. So if you know these basic things, this is computationally pretty easy, pretty quick to figure out. Let's do another one. this is question 6 here. In the T-series of f of x equals log x at a is equal to 2, the coefficient of x minus 2 to the 3 is, and then we have a bunch of options. So let's not write them out. Let's just figure out what the coefficient is. Okay, so solution. So this is our function. We need to find the coefficient in front of this term of the T-series. So let's just remind ourselves the general T-series around a equals 2. So we know that f of x is the sum from k equals 0 to infinity, kth derivative of 2 over k factorial x minus 2 to the k. Right? This is the general expression. If you write out the first few terms, we have f of 2 plus f prime of 2 x minus 2. Again, this is the first two terms are just the tangent line, and then we have s2 squared. And what are we looking for? We're looking for the power 3. So this power 3 coefficient is like this. So it's 2 factorial is 2, which is right like this, but 3 factorial is going to be 6. But let's write 3 factorial x minus 2 to the 3, and then we have all these other terms like this. Cool. So our job is to find out the coefficient in front of x minus 2 to the 3, which is exactly this coefficient. So I need to calculate the third derivative. There should be 2, not x, at 2 over 3 factorial. Yeah? And once we've done that, that clearly is exactly what we're looking for, right? So then it's just differentiation. So this is our function, right? So f prime of x is just 1 over x. F double prime of x is minus 1 over x squared. And the third derivative is just 2 over x to the 3. Yeah? Cool. So I've got to stick in the value. Little prime of 2 is 2 over 2 to the 3, which is 8, so it's going to be 1 over 4. Right? But then, where is the thing? This guy. So 3 factorial is 3 times 2 times 1, so 3 times 2 is 6. So then this thing, f double prime of 2 over 3 factorial, is going to be 1 over 4 times 6, right? Which is 1 over 24. That should be our answer. Yep, that is option C. Cool. All right. Let's do the next one. Okay, this is question 7. Maybe I can put it down here. So which is the coefficient of the x to the 31 term in the power series around 0 of this function. f of x equals x over 3 plus 4 x squared. Okay, so what is this testing? So we're going to have to expand this in a Maclaurin series as a power series centered around 0. And we're going to have to find the coefficient in front of the 31st term, right? Now, what is cool about this guy is that this guy is something which, with some algebra, we can put in the form of 1 over 1 minus whatever, call it y. And then just use this representation of 1 over 1 minus y is the sum of the geometric series sum from k equals 0 to infinity y to the power k. So we can rather easily find the explicit Mach series of this expression, right? That'll be our strategy. Okay, first let us erase the board and then we'll get to work on it. F of x is this thing. And want term in front of x to 31. Okay. So, solution. Let us write it like this. Okay. Let us factor out a 3 from the bottom. And let's write minus 4 over 3 x squared. Okay. And then this guy, we can think of as the y in the 1 over 1 minus y. So we can write this out as x over 3, the sum from k equals 0 to infinity of minus 4 over 3 x squared to the k. And that's it. And then we just expand that out. And we're going to have minus 1 to the k, 4 to the k, 3 to the k, x to the 2k. And then we multiply through. So k equals 0 to infinity, minus 1 to the k, 4 to the k, 3 to the k plus 1, x to the 2k plus 1. Cool. K looks like an x. There we go. All right, so we want the term in front of x equals 31. So clearly that's going to happen when k equals 15, right? So if k equals 15, then what do we have? We're going to have minus 1 to the 15. So it's going to be minus 1, 4 to the 15, over 3 to the 16, and then just completeness right at this. So this will be what happens when k equals 15, right? So I'm going to put an if. So this is indeed the term in front of x to the 31. And what is this? This is minus 4 to the 15 over 3 to the 16. And that is option C. Okay, so all this is testing is your ability to remember how to get Mclaren series quickly from expressions like this, right? Cool. All right, let's do another one. Question 8. So it wants us to find this limit. The limit as x equals 0, to x to the 6 plus 3x squared over cosine 2x to the 3 minus 1 plus x to the 6. Okay. So we did a problem like this before. Let's do this again. So the point is that we know what the cosine of 2x to the 3 is as a Maclaurin series, right? Because we can just expand it out. So cosine of 2x to the 3, we're just going to put 2x to the 3 inside of the Mach series for cosine. So the Mach series for cosine is this, right? So it's minus 1 to the k, and then we're going to have 2x to the 3 to the 2k over 2k factorial, right? And then what's that? That's the sum. K equals 0 to infinity, minus 1 to the k, and let's take the 2 through so that we're going to have 4 to the k, and then we're going to have x to the 6k over 2k factorial, and let's write out the first few terms. So when k equals 0, we're just going to have 1, 1, x to the 0 is 1, 0 factorial is 1, so the first term is 1. When k equals 1, we're going to have minus 1, 4 times this, and then 2 factorial is just 2, so we're just going to have minus 2x to the 6. And that's all we really care about, because the other terms are going to be higher order terms of x, right? The next one will be something of order 12, and the next one will be something of order 18 and whatever. And we don't care about those, because when we put them inside this expression, they will just be terms that go to 0 way faster than anything else on the bottom, right? So I could write some stuff. Let me write some stuff. If I write the coefficient, then I'm going to think about it, and I don't really need to think about it. So I'm just going to write O of x to the 12, which means that everything to the right will be of order of x to the 12. It'll be of the size of x to the 12, more or less, with some coefficient in front or smaller, right? So when I put it into this expression here, so okay, then I'm only going to care about these first two terms, and I'm going to have the 1 cancels, and I'm going to have just minus x to the 6, because I get a plus x to the power 6 from this. So it's going to be 2x to the 6 plus 3x squared, and then I'm just going to have minus x to the 6, and then some other terms, but they're of order x to the 12, and I don't care what they are, right? Because I'm taking the limit as x goes to 0. So the limit as x goes to 0 of this expression, I think I don't want to rewrite it. Let's call this thing star, equals the limit as x goes to 0 of this thing, 2x to the 6 plus 3x squared minus x to the 6 plus, and again, this thing just represents all the terms of the Mclaren series that come after the x to the power 6. So it's going to be something x to the 12, something else x to the 18, something else x to the 26, and so on. And I don't care about any of them, because they're all going to be smaller than x to the 12, and they are just going to not be important, because for very small x, the x to the 6 is way, way, way bigger than x to the 12 or any of these other terms. So I just forget about them, right? So if I look at this, I realize something is wrong. Because I've written 2 and it should be 7. Okay. So if I look at this, then for very small x, then this x to the 7 is way, way smaller than this guy. This x to the 12 and all the other terms are way, way smaller than this guy. So this will just be the limit of the highest order term divided by the higher order term right here, right? So to be formal, we could factor out by x to the 6, take the limit, but we've done this lots of times before, so we're just going to cut to the chase. This thing will just be minus 2, and that will be our answer. Right? Let's see what option that is. That is option E. Cool. Let's do the next question. So compute derivative of f of x equals this at x equals 0. Okay. Solution. All right, cool. So obviously we're not going to differentiate this 102 times, right? So what we're going to use is the fact that the general Maclaurin series for f is given by this thing, right? Okay. So first two terms. F of 0, f prime of 0, x, f double prime of 0, over 2, x squared, and so on and so on. And somewhere down this list is the 102nd derivative, right? But we also know what the Mclaren series of this guy actually is, because it's e to the minus x squared, so we can just put minus x squared inside the Mclaren series for e. So f of x is also equal to the sum k equals 0 to infinity of minus x squared to the k over k factorial, which is the sum from k equals 0 to infinity of minus 1 to the k x to the 2k over k factorial, right? Cool. Now, what is really nice is that this equals this. It's the same function, right, over its interval of convergence, and happens that this thing converges for all x. Okay, so let's write that as a separate line. So we have that this thing, the sum from k equals 0 to infinity, f to the k is 0, x to the k over k factorial is equal to, let's change color, this thing. And now we're going to change, we're not going to write k now, we're going to use n. N equals 0 to infinity, minus 1 to the n, x to the 2n over n factorial, because whether you use k or n, it's exactly the same thing, right? Cool. So recall that if we were talking about polynomials, so suppose we had, say, ax squared plus bx plus c was, say, 2x squared plus 3x plus 1, right? Then you guys would be very happy in telling me that c is 1, b is 3, and a is 2, and you'd come up with this pretty fast, right? And one way to do this would say, okay, we're just at x equals 0, and then we have to have c is equal to 1, and then we could differentiate this equation on both sides, and then we'd kill off the constant terms, And then we'd set x equals 0 again and kill off the quadratic, what would then be the linear terms, and we'd compare b and this term, which would be 3. So this, we differentiate again, x equals 0, and we get the a is equal to 2. Right? So this thing you guys would be fine with. This is the same thing. This is the same thing, except that we don't have a quadratic, we have a power series. But again, a power series is just as good as a polynomial in the interval of convergence. Right? Cool. So the only way this is possible is if every order of x, the coefficient in front on this side is equal to the same coefficient in front on this side. Right? And what we're particularly interested in is the coefficient on the left-hand side in front of the x to the 101 power, because for that guy we have the 102, the x 102, because for x is, the k is 102, because for k is 102 we see the 102nd derivative inside this, right? So in here, if we have k is 102, then what do we see? We see f of 102 of 0 over 102 factorial x to the 102, right? Cool. And that is some particular power inside this power series. Yeah? But if we look on the right-hand side, then for n is 51, we have that we're going to have minus 1 to the 51, which will be odd, and then we'll have 51 times 2, which is 102, x to the 102, and then we're going to have 51 factorial here, right? And these are individual powers of x, right? There are a whole bunch of other ones, but we know that the coefficients in front of them have to agree, just because of exactly that, right? So since this power series equals that power series over some range of x, that's only possible if the coefficients in front, which means this thing right here, has to be equal to this thing right here. Yeah, there's no other way we can have it. There's no other way this can be true unless this is true. So this thing implies this thing. Okay? So in particular, that means that, let's just write it again, f of 102 at 0, and if we multiply on the other side, so we're going to have, so this is just minus 1, so minus 1, 102 factorial over 51 factorial. Right? And let's just get rid of this, we'll just call it minus. So this has to be the case, right? Let's go through the steps. What did we do? So it's asked us to find the 102nd derivative of this guy, okay? We're going to use the fact that we have the Mclaren series, okay, whose coefficients in front of the powers of x are given in terms of orders of derivative, right? So in front of the x to the power 102 is f, taken the derivative of 102 divided by 102 factorial, right? Yeah? That is this thing. And we know what the exact expressions of the Maclaurin series coefficients have to be of this function, because we can just put it into our formula for the Maclaurin series of e to the x, right? Which is what we did here. So we have the coefficients, we have all the information explicit about what the coefficients are, and since they have to agree, that means we just compare them. So we're looking on this side, and we're looking on that side, and we know when k is equal to 102, we see this f to the 102 derivative here coming into the expression. And then when n equals 51, then we're going to get x to the 102, which is the right thing, and the coefficient in front will be minus 1 over 51 factorial, right? So this coefficient has to equal this coefficient, for exactly the same reason that when we look at this line, we know that b equals 3, for exactly the same reason this coefficient has to equal this coefficient. The only difference is that this is a quadratic, right? And the power of x is 1. This or D is a power series, and the power of X we're interested in is 102. But the principle is exactly the same. If you're happy with this, if you're happy that you can deduce B equals 3, there's nothing different here. This might look like a harder problem. There's more symbols, but it's the same thing. Yeah? Cool. So since the powers in front, the coefficients in front of the powers have to agree, this thing has to equal this thing, therefore we have the magic thing we've been looking for, the 102nd derivative of our function. It has to equal this. And that is I don't know what option that is. Oh, here it is. That is option B. Option B. Cool. So that looks like a slightly harder problem, but it isn't a harder problem if you keep your head. Right? So there's been a number of problems like this in homework. The fact that this problem is here in the practice problems means that there's a good chance you'll see something like this again. So make sure you can do this. Make sure you're happy with this. So don't just watch this explanation, go, okay, that sounds reasonable. Do this problem yourself. Hopefully you've already done this problem yourself. And make sure you can just find this coefficient, find this 102nd derivative by yourself by working through this kind of reasoning. Okay, that's it for today.